Okay, so error analysis of this second method. So I'm not doing the total derivation of that. I'm just giving you the true error. In this case will be minus f double prime xr upon factorial to f prime xr e at I and e at I minus 1, where e at I is nothing but xr minus xi. So in this case, error will propagate in this way, that error will be, of order of multiplication of errors of previous two iterations. So that is what error analysis of second method says, that the error in the current iteration will be of order of the multiplication of errors of previous two iterations. So that is the error analysis. Now I did not tell you that why second method is needed, because we already have, we already have the Newton-Raphson method. Since we already have the Newton-Raphson method, then what is the need of going for the new method, second method? The problem with Newton-Raphson method is that we require f prime x, and it is difficult to compute this for very complex functions. So it might not be easy every time to compute f prime x. Sometimes the function expression is so complex that it is very difficult to find out the derivative of it. So in those cases, the second method basically helps in finding the root, because we don't need the derivative at all. We just need the function value. So that if the derivative is not required, then the complexity is automatically reduced. So that is the idea why do we need this second method. And now with this second method also, there has been an update. That update is in the form of modified second method. That update is in the form of modified second method. And what does this modified second method says? That we can only work with single initial guess. So this says that we are not required to have two initial guesses. We can only work with one single guess, and we can take a perturbation in that single guess. So suppose xi is the guess, and we can take delta x, that is the very small number, that is the perturbation. So we will calculate f of f prime xi as f of xi plus delta xi, and this delta xi might vary with iteration, or this might be constant with iteration. We can control it, this delta value. So suppose if I have reached in the iteration, if the value has reached 10 to the power minus 4 and still I am using delta of 0, 10 to the power minus 2, then there is no point of doing that, because the delta has to be, so I'm just giving you a rough estimate that delta should be of order of 10 to the power minus 3 times x. So just remember this. This is not a rule. This is just a, just to give you an idea that what should be the order of this delta, or you can take it of lower order. You can take it of 10 to the minus 2 also, but the delta should, it's a very small number as compared to xi. So that's what I mean to say, that it has to change with the iteration. You cannot keep delta x as same. you can keep delta x as same if the value is not changing with the iteration. So that is in your control. Delta x is in your control. It is not something which has got some formula to derive. So the derivative will be calculated as f prime xi, that will be equal to f of xi plus delta xi minus f of xi upon delta xi. I hope I am clear. I am taking this single guess and one very small number. And from Newton raphson or from secant method, we had this formula xi plus 1 is equal to xi minus f of xi upon f prime xi. And if I put the value of f prime xi as f of xi plus delta xi minus f of xi upon delta xi, then this expression becomes xi plus 1 is nothing but xi minus f of xi delta xi upon f of xi plus delta xi minus f of xi. So this will be my formula to update the value of x in this modified secant method. So it's a update of the secant method. So my battery is low. I'll continue with the next video uh, with a new method that is called Mueller method. Thank you.